Modern enterprise software development operates under tight constraints. Engineering teams face constant pressure to ship new code quickly, while simultaneously ensuring that every release is secure against external threats. To navigate this, most teams default to the OWASP Top 10 as their primary security standard. The OWASP Top 10 is an awareness document. It categorizes the most common and critical security flaws, effectively giving developers a list of what to avoid. Building a security program around a list of known vulnerabilities forces an engineering culture to be reactive. Teams write code, test it against the list of common mistakes, and patch the flaws they happen to catch before deployment. Knowing what to avoid does not mathematically or structurally prove that a system is actually secure. A lack of known errors is not the same as a verified defense. The OWASP Application Security Verification Standard, or ASVS, version 5.0 is designed to address this exact gap. Instead of a top 10 list, ASVS provides approximately 350 specific, testable security requirements. This framework shifts application security away from following abstract principles and moves it towards implementing concrete, verifiable engineering controls. By defining exactly what must be verified, ASVS turns application security from a reactive post-mortem exercise into a proactive, measurable systems engineering discipline. Massive security concepts, like secure session management, are too broad to test effectively. To prove a system is secure, these concepts must be broken down into atomic, trackable units. This diagram shows the syntax of an ASVS requirement. The string v5.0.0-2.1.3 divides into distinct segments identifying the version, chapter, section, and requirement number. Strict semantic versioning, tracking major, minor, and patch numbers, ensures every requirement remains uniquely traceable across releases and compliance audits. Version 5.0 introduces a dual structure, splitting these requirements into two distinct categories. The first category is documented security decisions. These capture the architectural intent and design rationale, explaining how controls are applied. The second category is implementation requirements. These dictate the specific, verifiable behaviors expected to execute in the compiled code. This dual structure forces engineering teams to bridge the gap between secure architectural theory and verifiable technical implementation. Applying 350 rigorous security checks to every single component of a modern application is logistically impossible for most teams. To organize the workload, this grid illustrates how ASVS 5.0 groups requirements into 17 modular chapters based on functional domains. These domains cover specific architectural components, like Chapter v3 for web frontends and v4 for APIs. Chapter v17 covers WebRTC, Web Real-Time Communication, an open framework enabling direct peer-to-peer video and audio streaming in browsers. The framework is modular by design. Organizations select only the chapters that apply directly to their specific architecture. If a team is building a pure back-end API service, they adopt the API chapter and entirely bypass the web front-end requirements. Modularity prevents wasted engineering cycles. Teams pay the verification cost only for the attack surfaces they actually expose to the internet. Even within a single application, risk is not distributed evenly. Different components handle data with vastly different sensitivities. This chart illustrates the 3 verification levels of ASVS, scaling the depth of security testing based on risk. Level 1 is the minimum baseline, containing roughly 20% of requirements, focusing on preventing common high-impact flaws. Level 2 is the recommended default for enterprise applications managing sensitive data. Level 3 is the high-assurance tier, requiring deep manual review for critical infrastructure like online banking, where failure has severe consequences. The verification levels are cumulative. Achieving Level 2 inherently means passing all Level 1 requirements. Organizations can mix these risk levels within the same system. A standard public-facing API endpoint might be scoped to Level 2, while the back-end identity management service verifying those API requests is held to the stricter Level 3 standard. By aligning the verification tier directly with business risk, organizations invest their security resources where they deliver the greatest return. Relying entirely on manual security audits creates severe validation bottlenecks that are incompatible with modern, rapid deployment schedules. Because ASVS requirements are atomic and uniquely identified, they are ideal candidates for automated testing. This diagram outlines a continuous integration and deployment workflow. Between 60 to 70% of ASVS baseline requirements can be fully automated within this system. Level 1 and 2 controls translate directly into testing and scanning scripts that run automatically. This creates an immediate feedback loop. Developers receive automated alerts for testable failures before the code ever reaches a release state. Offloading these baseline checks to automated systems frees up expert security personnel to focus their time on complex, manual Level 3 threat modeling. Automation transforms ASVS from a static compliance document into a continuous, active gateway for engineering quality. Managing multiple overlapping standards and compliance mandates often leads to framework fatigue within an organization. This diagram illustrates the macro to micro ecosystem. At the macro layer, NIST and CIS dictate organization-wide governance. At the process layer, OWASP SAMM measures software lifecycle maturity. Finally, at the micro layer, ASVS provides granular specifications proving code is structurally sound. Mapping ASVS implementation results back to NIST or CIS controls creates an unbroken chain of evidence, connecting raw code to executive compliance audits. ASVS provides the sharp, measurable edge that proves an organization's high-level security governance is actually working in production.